Hi everyone, this is Michal, and in today's episode we'll go through 9 of the most recent questions from meteorology, and we'll go a bit more in depth into the questions as we always do. So let's jump into the first question, which is, in the case of blowing snow, visibility may reduce to a minimum value of. So what you need to know when it comes to visibility in aviation, and especially during the meteorology exam, is that the snow is the worst when it comes to visibility. So snow will always give you worse visibility than fog, haze, or any other precipitation such as rain. And in case of blowing snow, this is when the snow is being blown close to the ground. The visibility can get essentially down to zero. In aviation, officially in meteorology, we recognize that blowing snow can decrease the visibility from 1 all the way to 50 meters is the range for blowing snow. Then we have heavy snow, which will be 50 to 200, and then moderate snow, which will be up to 1000 visibility. Of course, then we have other different types of visibility affecting phenomena such as smoke, haze, mist, and fog. And here I want to point out the two, which are fog and mist, as I'm sure this question can come up in math very often. So what is the difference between fog and mist? And the big difference is that fog is visibility reduced below 1000 meters, and and mist is below 1000 and 5000 meters. But both of these are linked to water droplets being suspended in the air, or essentially low clouds. But that's it for the reducing visibility and blowing snow. And for question number 2, so by use of Doppler techniques, modern airborne weather radar can detect turbulence. And so, of course, the modern airborne weather radars, they used the short frequency band. This is because they are the best to reflect from other particles. And this is a keyword here, reflect. Of course, the weather radars work on the principle of any radar. So they send out a signal and then they collect the reflected signal, and they can see how far a certain precipitation or objects are. And the Doppler technique is nothing else but a computer that can sense the frequency changes in the return signals. And these frequency changes are linked to objects' movement. So if an object is moving, then the frequency of the return beam will be different. And the difference can be deciphered by a computer or some elaborate calculations into a speed or the direction of movement. So the airborne weather radar that uses a Doppler technique can tell us where a turbulence is, because it can sense the movement of the reflected particles, and most often this will be rain. As remember for the exams that snow reflects the radar very poorly, and water droplets reflect it very well. So this turbulence can be detected in thunderstorms because we need something that can be reflected. Clear air turbulence is only really reported by pilots, and this is how we know where it is. There is no clear and good way of detecting clear air turbulence, unfortunately. For question number 3, the Harmattan. And so the Harmattan is one of the winds that we need to know for the exams. The Harmattan will be a wind blowing in Africa. So with the Harmattan, think about sand, think about the decreased visibility. When the Harmattan is blowing, then most often the visibility will decrease for sometimes days to come, so up to a week, because of the suspended sand and dust that comes with it. It blows down from the Sahara, depending on the season. And this will be a northeastern wind affecting Northwest Africa during November to April. So during the winter in Europe, and this will reduce visibility in rising dusts, like I mentioned, sometimes for days to come. Other honorable mentions, so the winds, when it comes to them, are of course Pamperos, Bora, Mistral, and Foehn winds, which we all need to know, and these all unfortunately need to be studied. Some keywords to give you here: Bora will be associated with the Balkans and the Adriatic. And then Pamperos is a wind that's blowing from Antarctica all over the South America. And lastly, Mistral, which is blown down to Rhone Valley, for example, very often in France. This is a wind that persists there. For question number 4, what weather conditions in the region of the Alps would you expect with Foehn wind from south? So again, the Foehn wind. So the Foehn can have many names. It's called, for example, Chinook in northern Canada and the States. And all Foehn wind is a wind is a parcel of air, and this is usually moist air that's being blown up to a mountain. And as it's pushed up a mountain, up and slope, and where it starts to adiabatically cool down, and at some point the air will reach its saturation point, and the precipitation will start as the parcel of air then continues to rise, as it continues to be pushed. After reaching saturation, it will create clouds, and as I mentioned, the rain will start to go down, so the moisture and humidity of this air will start decreasing, and also it will start moving upwards with and cooling down with a different lapse rate. So before it was a different lapse rate, and then it is a saturated lapse rate, so sour. And what this does, that as it reaches the top of the mountain, the clouds will start to form later. So you always have on the upwind lower cloud base than on the downwind. And then once the wind goes down, it is usually much less humid, so it will be a dry and a warm wind because it cools katabatically as it is being pushed down. So in this case, we will expect the wind to bring heavy turbulence on the northern side. It will be turbulent on the northern side, on the lee side, but it will not be turbulent on the southern side, on the upwind side. Clouds on the southern side will pass in the Alps. Yes, the clouds will be on the southern side, and there will be no clouds on the northern. Strong winds will be on the northern as well, and A-frame icing conditions on the northern side as well. Not the clouds will persist on the southern side where the wind is being pushed down and the air. For question number 5, so the validity of a routine TAF is. So this question can be quite tricky sometimes. However, it's good to remember that a TAF has no fixed validity of a routine TAF. It will be stated in the TAF itself. However, the TAFs will be valid anywhere from 6 to maximum of 30 hours. And so it cannot be valid for more. Here, it's also good to remember the validity of a METAR. So these questions come up quite often as well. However, remember that METAR has no fixed validity. It is only valid during its issuance because a METAR is an observation. So once you see a METAR, this is weather reported at a given time at a given airport or a meteorological station. So any later than that, the METAR will not be really true. TAF is, of course, a forecast. So these forecasts will be valid for longer and will be relevant for longer. If a forecast changes between METARs, a SPECI can be issued, which is a special METAR to amend the weather if it changes dramatically between 20 or 30 minutes between each METAR when they are issued. And so here another question, and this question asks us about the Venturi effect, so flying through the valley. So what will happen when we're flying through the valley? And this is the image for you to see. So of course, as you're flying between the two mountains into the valley, just like in principles of flights, the Venturi effect will take place here. So as the area decreases, the speed in order to maintain the mass flow will increase. And as we increase the speed, the static pressure will drop. And as you know from the mnemonic, from high to low, so from high pressure to low pressure, watch out below. This means that our true altitude, indicated altitude will be higher than our true altitude. So our true will be lower than indicated, and speed will be higher. Now for question number 7, so which of the following caused the formation of convective cloud structures close to the ITCZ, so the Intertropical Convergence Zone? And the Intertropical Convergence Zone is a place on our Earth where the Earth is tilted towards the sun at 90 degrees, so this is where the isolation is the highest, where the ground, so either the oceans, the seas, or the land, gets the most energy from the sun, meaning it heats up the most, and this is where the convective currents are the biggest. This is also the place where the convergence, the trade winds converge, and this also amplifies this effect as we have almost only vertical movements of air, and sailors call these places doldrums actually because there is almost no horizontal air all the way there. And of course, the trade winds that are coming from south or north, they are collecting moisture as they drop down, and this moisture then feeds big convective clouds and squall lines that can be seen close to the ITCZ. And this will make answers 1 and 2 most correct. In the subtropical highs that are on 30 latitude, we have mostly dry weather, and easterly jet streams will not really play a role here, as the jet streams only affect the upper levels of the atmosphere. Now referring into this annex, which option best describes the meteorological feature at location V? So I'll open it here, and in order for us to not look far, this is the location V. So this is the phenomena that we need to decipher. So what is this? We know this is an occlusion. This is where the cold front catches up to the warm front, and we can have a cold or a warm occlusion. And the difference between the two is whether the air is going on top of the colder or below of the colder air. And in this case, you need to remember that a cold occlusion, uh, as this is the one, will always have an occlusion on the elongated line from the front. So in this case, the elongated line comes from the cold front line. And if it was elongated from the warm front line, then we would talk about warm occlusion. So in this case, this will be a cold occlusion. And remember that occlusions are a big threat in aviation because they can bring embedded thunderstorms. So it's vital that you fly with a radar. And if you can, then of course, always avoid these. And lastly, the question number 9, in the atmosphere, what contributes to initiate the condensation process? And there's a rule of thumb which essentially says that water vapor requires a surface in order for water to change phases and change its states. So without a surface, water vapor cannot really condensate. And this is where the condensation nuclei come in for the clouds just to be able to form, as well as, and mainly, the precipitation to start forming. And these condensation nuclei are very tiny particles of dust or sand or any other physical surfaces, or maybe other water droplets that are very, very tiny, on top of which the water can start connecting to each other, creating bigger droplets and condensating. So these will be micrometric solid and low liquid particles. And this is also why when you have dusty, hazy weather, we can expect some light precipitation, as these nuclei are very common in that case, in that space, especially if the weather is humid and we can have some other convective activities, then that is a recipe for disaster. But this will be everything for today. So all the questions that we just saw have been seen in the recent exam. I hope this was helpful. If you have any questions, always feel free to reach out to us. But for now, thank you for tuning in, and I hope to see you during a next video. Have a fantastic night and good studying. Bye-bye.